for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful Corvette? It all depends on your point of view. One thing is for sure, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box.
The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This standard electronic engine controls training module covers the General Motors electronic engine control system. In order to confidently and profitably repair these systems, the mechanic must have certain hand tools and test equipment. Also, he should have a working knowledge of the basics of electronic engine controls and an understanding of GM computer command control. And most important, he should be familiar with the electrical and electronic diagnostic procedures.
Let's briefly review some general aspects of GM electronic engine control. Then we will diagnose some on-vehicle problems using the GM diagnostic system and some simple test equipment. Ready?
General Motors, as you well know, has gone through an endless series of changes in their electronic ignition systems since the middle 70s. First, the HEI, High Energy Ignition Systems. You remember that big distributor with the fat spark plug wires. One of the first electronic ignition modules was bolted inside the distributor. I'm sure you remember one of the first diagnostic headaches, trying to figure out why the car had a hesitation. You and everyone else probably thought it was the accelerator pump. It turned out to be a broken lead wire in the magnetic pickup. The system was actually very simple. A magnetic pickup that generated a voltage signal as its armature rotated inside the pickup assembly. This mechanism replaced the old points and condenser. A microprocessor in a chip was bolted inside the distributor. The circuit chip actually controlled the current flow through the primary side of the ignition coil. This module controlled dwell and the resultant ignition timing. The system worked well until more stringent emission and fuel mileage standards were mandated by the federal government. The engineering response, of course, was more sophisticated electronics. Between Cadillac, Buick, Oldsmobile, Pontiac, and Chevrolet, an endless series of modifications to the ignition system took place. Mizar, ESC, EST, ESS, EMR, and even an EST-ESC combination. And now we have DI, C3I, DIS, IDI. So how do you sort out all of these systems? For our discussion during this videotape, we are going to forget all about the false starts GM introduced on their way to the first widely used electronic engine control system, Computer Command Control, or CCC. This system was introduced in 1981 on all GM brands. It uses an electronic microprocessor or computer, which is called the ECM. Until direct ignition, the familiar HEI-style ignition module continued to be used, though its control was adapted to the ECM. The CCC system uses various engine and environmental inputs, which vary from year to year and model to model. Their sensor inputs can include a throttle position sensor, TPS, engine temperature, CTS, RPM and cylinder position signals from the distributor, crank sensor or cam sensor, intake air temperature, mass airflow, MAP, manifold absolute pressure, or input on vacuum and barometric pressure, VSS, vehicle speed sensor, a NOx sensor, and a series of miscellaneous switches including AC, power steering, alternator, etc. Utilizing these sensor inputs along with pre-programmed memory and memory from a PROM, programmable read-only memory unit, the computer responds with outputs to various controlling devices for the fuel system, the emission system, and/or the ignition system, as well as a diagnostic output to display a check engine light or service engine soon light on the instrument panel. Next, let's quickly take a comparative look at a few of the more common types of General Motors systems before we begin diagnostics. Just like the early non-computer systems, the magnetic pickup still signals the ignition module to control the ignition coil's primary windings. It is a very simple device. Inside the magnetic pickup is a timing core that is connected to the distributor shaft. As the timing core rotates inside the pickup assembly's coil of wire, it causes the generation of an AC voltage signal. The AC signal output is sent to the ignition control module. There, it ultimately triggers a switching transistor. The module then controls the ignition coil's primary current flow, and thus the timing of spark plug firing. Simple. In CCC, the magnetic pickup still supplies the triggering signal to the ignition control module, but the module's control of ignition timing now only functions during cranking, as the engine is started, normally under approximately 400 RPM. Though the magnetic pickup still supplies the ignition module with base timing signals, it also sends sync pulses to the ECM, which establishes cylinder positioning for EST to function, and in the case of fuel injection, to control the injection pulses. As the engine starts, the ignition module electronically converts or steps out of the timing control picture, and the engine control computer, or ECM, takes over the timing of the engine and the control of the fuel injectors. The ECM uses signals from barometric pressure, or MAP, coolant temperature, RPM, and engine load to control the ignition timing. Remember, load can also be established from a MAF sensor on fuel-injected engines. This basic circuit design has been utilized until the introduction of direct ignition, except with two minor modifications. In 1982, Chevrolet's 229 cubic inch engine and some GM 2.5-liter fuel-injected engines utilized a Hall effect switch, in addition to a magnetic pickup. The Hall effect switch was added to the primary ignition circuit to permit the use of electronic control of the ignition timing, because the V6 engine was in odd-fire configuration. On the four-cylinder engine, it also controls firing of the fuel injection. The Hall effect switch is inside of the distributor. It is mounted directly above the magnetic pickup. The other variation in electronic control of timing or electronic spark timing is ESC, electronic spark control. When this is used on the CCC system, there is no variation in the EST circuit under normal operation. The system works as we have discussed. On those engines with ESC, two additional components have been added: an ESC control module and a knock sensor. When the knock sensor hears a noise in the engine, a signal is supplied to the ESC module. The normal EST signal is wired through the ESC module and usually passes through unaltered. But when an input from the knock sensor is received at the ESC controller, ESC overrides the normal timing control of the ECM. The system can retard timing as much as 20 degrees in some applications. Retard is done in 2-degree intervals per second until the knock is gone. After a period of time, it allows timing back in 1-degree intervals until knock is again heard, and of course then retards timing again. Before we begin diagnostics, let's take a quick look at direct ignition. Subsequent video training programs will deal with direct ignition more deeply. It could be called DI, C3I, DIS, or IDI. General Motors has 3 different systems as of 1989, and I'm sure others will follow, but they all operate on the same basic principle, that is, elimination of the distributor. One style even eliminates the spark plug wires. This Pontiac has a Quad 4. It contains one example of the direct ignition called IDI. Under the protective cover is the coil pack and the ignition control module. Note, the system does not use spark plug wires per se. The coil and the plugs connect through a small coil spring conductor and are insulated by very heavy boots. This Pontiac illustrates a second style of GM direct ignition system. Here, the ignition module bolts under the coil pack. The function of the system is quite simple. Each system uses one coil for each set of 2 spark plugs, 2 coils for the 4-cylinder engines or 3 for the 6-cylinder engines. The engine control system still needs a timing or reference pulse to understand the location of the various cylinders and the RPM of the engine. The needed information, sensor input, is supplied to the computer using either a Hall effect or magnetic pickup unit. Depending on the engine configuration, the sensor can be found either at the crank dampener, on the crankshaft, or at the camshaft sprocket. On the 3 and 3.3 liter engines, for example, both sensors are mounted on the crank dampener. One supplies the ECM with RPM information, called 1x. The other, a reference pulse for cylinder position, called 3x. The computer does its normal routine and responds by controlling the current flow through the multiple ignition coils windings to fire the spark plugs. On the 3.8 liter engine, both crank and cam sensors are used. Here, the cam sensor signals location of number 1 cylinder for spark initiation and sequential injection firing. On startup, number 6 injector and ignition for cylinders 3 and 6 must function in synchronization. The crank sensor signals the ECM on RPM. The cam triggers reference pulse for ignition and sequential injection on startup. You can see from this illustration that the 3 ignition coils take on a different appearance, but they function the same way. Also, remember that each coil fires 2 spark plugs. The majority of the spark energy is used to fire the plug that is on the compression stroke. The waste spark, as it is called, fires the spark plug whose cylinder is also at top dead center, but on the exhaust stroke. General Motors adds more confusion to DI by referencing a Type 1 and Type 2 systems. Type 1 utilizes an ignition coil pack that has 3 plug terminals on one side and 3 on the other. The control module bolted below the coil pack has 2 fuses. The system is used primarily on 3-liter and 3.8-liter engines. The Type 2 style is used on the 3.8-liter engines only and has all 6 spark plug wires in a row. Its module has only 1 fuse. What this means to you is that parts are not interchangeable and diagnostic procedures are different. If you're not sure, consult specific service literature before you proceed with particular diagnostic steps.
That's it. We've covered the basic components of the GM system. Now, to repair some common problems. Hands-on experience may be the best teacher, but through the use of video, we can simulate almost everything, except your hands actually touching the components. With some simple hand tools and a few pieces of test equipment, any problem can be solved. Let's take a closer look.
Since 2 types of systems have been utilized, one having a distributor and the other a direct ignition system, let's begin by repairing the most common style system. This General Motors Caprice is a prime example of the majority of the CCC systems you will see for a few years. It utilizes a throttle body injection system, the early style computer, and it also contains an EST-ESC circuit. The owner's complaint is that the check engine light is illuminated. The car has been giving extremely poor fuel mileage and not running the way it used to. It also knocks badly on acceleration. Your first problem is deciding whether the condition is fuel-related or ignition-related. Obviously, it could be any number of things. To quickly and profitably repair the problem, you will need to follow a logical approach to troubleshooting. The first step to a successful repair is to derive some general information, particularly the VIN code and the exact details of the complaint. Remember, you are looking for the 8th digit and the 10th digit for proper information. Don't make an error. Double-check the VIN code. The 8th digit indicates the engine type and make, and the 10th indicates the exact year of the car. Whatever you do, don't guess. Ask the customer the questions necessary to determine exactly what his complaints are and when they occur. Remember, You cannot diagnose a problem that doesn't exist. Next, do a visual inspection. Check the spark plug wires, the air filter, battery terminals, and voltage, output of the charging system, the coolant level, antifreeze quantity, and check the operation of the engine's cooling fan. You're checking for the obvious. With the necessary information on hand and the visual inspection complete, your next problem is to isolate the system that is causing the problem. This can be accomplished using either an engine analyzer, handheld test equipment, or the onboard diagnostic system in the vehicle. Since we have a check engine light illuminated on the dashboard and we have a fairly good idea that the customer's complaint is fuel-related, we can use either of the two methods to check for trouble codes, a scan tool or the onboard system and dash light. Let's begin by deriving diagnostic codes utilizing the onboard system. The diagnostic plug is located under the dashboard. Utilizing this simple little tool or a jumper wire, ground the diagnostic terminal, that is A to B. Turn on the ignition key and count the flashes of the check engine light. You will first get a code 12, which tells us the system is capable of testing itself. It will repeat 3 times. A code 15. This signifies an engine coolant temperature sensor problem. We also have a code 42. Service literature lists this as a problem with the electronic spark timing circuit. This is all the information we can expect to derive from the check engine light. 2 trouble codes. Without a scan tool, you can't actually derive any additional data, but we can check out the components. Check service specifications and wiring schematics for details and component location. We know that the engine coolant temperature sensor is nothing but a thermistor, that is, a variable resistor. As the temperature changes, resistance changes. The computer plots or calculates this temperature. Utilizing a volt-ohm meter and a specification chart, we can check the resistance of the CTS and determine if it is in the proper operating range. With a scan tool connected, we would see that it's obviously reading cold. This unit is no good and should be replaced. If you recall the basics of the GM system, the coolant temperature sensor is one of the main components involved in the information string for switching the system from open loop to closed loop fuel mode. If it is supplying the computer an erroneous temperature signal, the fuel curve will be wrong. With the scan tool, it would be easy to check this by reading O2 voltage and cross counts. If the sensor were to check properly, the next test would be the source voltage from the ECM, the connector itself, and the signal line back to the ECM. Each of these tests would be performed quite simply by utilizing the volt-ohm meter until the source of the code 15 was isolated. Replacement of the CTS is a simple mechanical procedure which we don't need to cover during this program. The next problem is an EST-ESC circuit problem, code 42. Let's eliminate the ESC circuit first. Remember that this circuit might be considered as being placed in series with the EST and the ignition control module. The knock sensor signals the ESC module to delay spark timing. On this 4.3-liter engine, it is a simple system to check. The base timing test terminal should retard the ignition timing to the base timing point with the engine running. Next, to pinpoint the problem. The EST-ESC circuit is quite simple. Ignition power is supplied on terminal F of the ESC module. Terminal K is grounded, and the knock sensor signal is supplied on terminal B. If the engine is running and there's no knock present, the voltage on terminal L to the ECM should be between 8 and 10 volts. If the knock sensor sends a signal to terminal B, the ESC module lowers the voltage on terminal L of the ECM, and the EST circuit retards spark timing. A malfunction in the ESC controller or loss of ground at terminal K would result in a no retard situation, and cause the knock that the driver is experiencing. That's the problem, a bad ESC module. It is a simple matter to remove and replace the ESC module, then recheck the circuit. With the two problems corrected on this caprice, you should clear the diagnostic codes by removing the power fuse to the ECM for approximately 10 seconds. It is also permissible to disconnect the negative battery terminal for a period of time and then reconnect it. Now, let's take a closer look at the problem with this Pontiac 3.8-liter direct ignition system. The complaint is that the engine won't start. The engine cranks but will not start. Since this is a port fuel-injected engine, it is pretty difficult to see if we have fuel present. Since we have no distributor, it might appear difficult to check for spark, but don't be fooled. You can diagnose this vehicle by using the onboard system and dash light. You can also use a scan tool, and in both cases, you will use other handheld test equipment, fuel pressure gauges, volt-ohm meter, etc. We can proceed next to derive any trouble codes in the system memory. Since you already know how to use the onboard system, let's connect a scan tool to derive diagnostic codes. Plug the tool into the diagnostic ALCL connector under the dash. Power the unit from the cigarette lighter or battery. Follow the particular manufacturer's specifications for scan tool setup. Then read out the codes. A code 41. Cylinder selection error. A code 41 cannot be further diagnosed with the scan tool. No additional data can be retrieved. Follow this procedure to check out the no start problem. Check for fuel pressure, then spark. Connect a pressure gauge to the rail test port and turn on the key. Fuel pressure is present. Checking for spark is also a simple task, but you should observe caution since the coil's spark voltage is very high and at a much higher amperage than older systems. A simple spark test can be performed by using a spark tester or by installing a small piece of vacuum hose. Connect it between the spark plug terminals of the coil pack and the spark plug lead. Utilizing a screwdriver and a short test lead, ground the screwdriver. Do not touch the metal part of the screwdriver with your hands. Place the screwdriver adjacent to the vacuum hose and have an associate crank the engine. The next step is to determine why there is no spark. Is it a signal to the engine computer? The computer itself? An ignition module? All good questions. Let's do another simple test that helps isolate the problem. Disconnect one of the fuel injectors. Install a test light and ground it. Crank the engine and observe the test light. The light does not blink. What affects both the fuel injection pulses and the ignition system? On this engine, the camshaft sensor. On engines with dual crankshaft sensors like the 3.0 and 3.3 engine, it could be one of the crank sensors. Disconnect the camshaft lead harness connector and let's test the unit and the voltage signal. A quick test can be performed by momentarily connecting a jumper across the camshaft sensor harness and turning on the ignition switch. As the engine cranks, observe the fuel injector test light. The light blinks. Well, we have at least isolated the problem to the camshaft sensor circuit. Next, checking service literature shows that we should check the voltage available for the cam sensor. It should be approximately 10 volts on terminal C of the harness. With voltage OK, we have a defective cam sensor. That's it. We have repaired some problems on the two types of General Motors computer-controlled ignition systems. Don't be concerned about working on the direct ignition systems. They are easier in many respects than the older systems. Just remember that those vehicles equipped with the P4 computer have the ability to run extremely well, even if a component sensor has failed. If engines with a P4 computer have a diagnostic light, regardless of how well the engine runs, it warrants further checking of the system and component testing to isolate the specific problem.
This concludes working on GM electronic engine control. As you've seen, it's easy to troubleshoot and repair the system. I would like to take this opportunity on behalf of Standard Motor Products and its training department to thank you for purchasing this program, and we hope you will consider us for your future replacement parts needs.